First, we will just go with few of my slides, and then we will see some examples, and then we will discuss. If you have any questions, you can shoot. So MicroPython, basically, it's a lean implementation of Python 3. So we don't say this is as a subset of Python 3, but we say it's a lean and efficient implementation of Python 3. The reason is it's having some added features which is not there in Python 3, because it's going to run inside the microcontroller and it is going to interact with the hardware. Hardware interaction means it's not just going to interact with the register levels. It is having the capabilities to access each and every register of the hardware, like how we do using the C code. And advantage we'll see later. The next feature, it supports REPL. So REPL stands for read, print, eval, and loop. The way, whenever you are using a DOS command prompt, or whenever you are using a Linux command prompt, so everything works on REPL principle. So where you just type something, so it takes the data as input, then it evaluates it, do some background check, background evaluation based on what kind of operation command you have typed. So it do the evaluation and then it prints the result. And then once again, it gets into the prompt mode. So you can enter the next command. So that's a very useful feature. So generally, Python supports REPL, and the same feature has been taken into the MicroPython as well. So this is very cool feature where in the runtime, it allows, and this is the first time it is allowing the users to interact with the microcontroller. Prior to this, there were no ways that a user can interact with the microcontroller in this way. We used to have a serial port, and we used to implement certain command, and based on those commands, certain operations were performed, but it was not REPL. In STM32, it allows, as I told you, it allows in real time the users to interact with the microcontroller. For example, you can control a GPIO, you can control any sensor, you can read the sensor data, and you can even perform certain arithmetical and logical operations. So let's see the architecture of MicroPython. So this is a very simple and very high level architecture of MicroPython. So basically, it is divided into two layers. The upper one is the application layer. So it basically holds your scripts. So whenever we develop all the application using the script, we place into the application layer, which is appearing to us as a file system. The bottom layer, which is shown in a blue color, is basically the we can say this is a C layer, or you can say this as a kernel layer also. So in this layer, we have multiple blocks. So some high-level blocks I have shown here. The first one is the AMCAL, then middleware, MicroPython, and kernel. So we'll see what is exactly the MicroPython block is. So all of us know the MicroPython basically is derived from Python. So Python itself is a interpreter language. It's not a programming language. So it's basically an interpreter. So that interpreter is there in this black block. So let's talk about the middleware. So middleware is something which is completely independent of hardware. So if we move from ST microcontroller to some other microcontroller or some other platform like Unix or somewhere else, so this code won't change. This code will remain like this. They may change in a condition when performance of the hardware changes. For example, in a high performing laptop, the middleware are basically it comes with added features. It will be having many more features. For example, when you are using different types of hard disk or SSDs, USB pen drives, so they all are having different type of file system. It may be NTFS, it may be FAT32, it may be ext4, ext3, or different type of file system. So these are very huge and thick um, layer of code. So definitely, those supports are not there here because this is meant for microcontroller. So we have modified this middleware, which will support only the embedded system and small microcontrollers. So this, at the moment, supports a very small, a tiny file system, which is based on FAT32 because FAT32 was meant for it is one of the most efficient and small file system meant for small embedded device. So we have modified the file system for microcontroller. And the storage, we can map SD card, but at the moment we are using one portion of our flash as a file as a storage device. And this file system is basically managing the files there in our flash. Uh, then one of the most important layer that's called microcontroller abstraction layer. So this is basically the drivers which basically helps us to drive the different peripherals of the microcontroller. For example, GPIO, PWM, UART, then USB, Ethernet. It can be anything like CAN. So everything has been abstracted within this AMCAL layer. So MicroPython interacts with AMCAL layer, and it basically provides you a very simple APIs, which basically you can either in one or two lines you can configure and make use of this. If we don't have this layer, then we have to write several lines of code to basically drive any output or to map any input or to map the interrupts. So the MicroPython, as we discussed, this is a layer of MicroPython interpreter, which converts the Python script into the machine readable instructions for the microcontroller, basically who is going to execute it. And it is having a small portion of garbage collector inside. So why we need a garbage collection here inside? Because this MicroPython is basically uh, it's running in a dynamic environment where we never know that what kind of application user is going to send us. So the whole concept is based on dynamic memory allocations. So we have a big heap, and user basically whenever they uh, write some application, the MicroPython will allocate memories and it will deallocate the memories. So randomly we keep on running the applications. So there is a possibility that it can get into the memory leak condition. So basically we need a garbage collection here. But because before this, no one has discussed about the garbage collection in the embedded environment. So since here we are going into basically a higher level language, so we are talking about the garbage collection here. So next. So what kind of support we have in STM32, and why it is efficient to use MicroPython in STM32? So STM32 basically produces a lots of high efficient microcontrollers. So if you will be seeing the H series of ST's microcontrollers, so they are basically running on 480, 550. The upcoming one will be running on like 600 plus megahertz. So these are really very fast microcontrollers comparison to the older one. If you go a decade back, so microcontrollers never used to run more than 150 megahertz. 150 megahertz was also more. when we started, we used to work on, like, if you go and see the mother of all microcontroller, like 8051, so it used to run on around 16 megahertz or 8 megahertz. But today, the speed of the microcontroller has been increased significantly. So, so it's good. We have lots of processing power. We have lots of memory space now. So, to make the deployment faster or prototyping faster, we are bringing the high-level language inside this environment to make the things faster. So, apart from this, if I compare STM32 with Arduino, so the hardware-wise, STM microcontrollers are much superior than Arduinos, because it's a, if you look into any of the ADCs, any of the DACs, so these are like very highly precised peripherals inside the controller, and the number of peripherals are also higher. Like if you see in a general uh, controllers of STM32, basically it provides you like approximately 8 to 16 timers. So same like 7 to 8 different ports, and each ports are minimum basically eight pins. So you get a lot of GPIOs, you get a lot of timers, you get even upcoming controllers are multi-core, and peripherals are very much highly precised. Like you get 24-bit, 16-bit ADCs, DAC. So this basically, I mean, this is the main reason the popularity of this microcontroller is huge. Most of the industries and hobby peoples are using ST's microcontroller. So yeah, so it basically allows you, easy access of GPIOs, timer, DAC, and PWM. So just instead of writing several lines of code, we can just in a couple of lines of code we can just write this. Uh, this application. So the advantage. So it's light and fast. It's very much lightweight. It can run on a microcontroller which is having just 16 KB of RAM and 256 KB of flash. So that's the minimum requirement. So if any microcontroller is having lesser than this, so then it won't be able to run there. So this is a minimum configuration we need for any microcontroller. Next is the support of the Python language. So basically, Python language keep on adding a lot of libraries. Its syntax are so easy and easy to remember, unlike C and assembly. So assembly was one of the most difficult programming language. C is much better, but it still need to learn a lots of syntax, and definitely we have to write several lines of code to perform a job. Performance wise, so it's a lean implementation of Python. So it's running on very fast devices. So we are able to get the real-time performance from the MicroPython. Next is the cross-platform compatibility. That makes it more popular because today, in every year you will be seeing that you will be getting a different flavor, different types of microcontroller. So once again, if you are coding in C, so you need to port the code from one controller to other controllers, and then you need to learn a lot about the hardware architecture, because you need to, because through code you are uh, I mean performing the low level operations. You need to know about all the peripherals. So here the porting is so fast. So you can basically just with a few lines of modification, you can just move the code from one controller to other controller. Only the thing is you need to just know that how many timers you are using. So suppose controller one is using 5 timers, and when you are moving the code from controller 1 to controller 2, and which that is supporting only 4 timers. So then if you're trying to run the code on the 5th timer, then it won't work on the next controller. So basically, those kind of things you just need to know. Apart from that, no need to know any drivers. Plus, uh, apart from the MicroPython implementation, it allows us, since it's an open source, it allows us to modify or enhance the uh, the support for new or additional hardware. So, for example, suppose tomorrow you get a new hardware, or you are trying to develop a product using the MicroPython, and you say, okay, this particular MicroPython is having a support only for evaluation board. So if I'm just going to add, say, like I'm going to add a NB-IoT hardware, which is working on SPI, or SPI, the serial peripheral interface, or suppose you want to enhance for USB devices, or suppose you want to enhance for PCI devices, or if you want to enhance for any networking devices. So it will allow you to develop the code for that. So the code can be developed in on various ways, not just on MicroPython. If you are comfortable to write C code, so you can enhance your code writing the C, because once again, the interpreter of Python or interpreter of MicroPython both are written in C language. Here also, the low level stuffs are written in C, but we have written the code for everything, so you can make use of any of those modules which is written in C. So in our example, we'll be seeing that how it can be done. So again, extensive libraries and modules. So MicroPython inbuilt is having, I mean, it's having so many inbuilt libraries. But apart from that, it supports a easily adding of the third-party libraries. For example, if you are familiar with Python, and you might have used NumPy for various calculations, mathematical operations, or many of us uses it for digital signal processing. So a small subset of that NumPy is available for MicroPython as well. So we'll be seeing that how we can quickly integrate NumPy into our MicroPython. And since it is meant for microcontrollers, so the power consumption is definitely very low. Whenever we put the MicroPython for any specific hardware, we keep in our mind uh, that we have to utilize the least power by switching off all the unused peripherals. Again, it's an open source, community support is there. So we have, I'll take you to the site where people keep on posting their own libraries, what they write, exactly like Linux. People keep on adding their support packages. So whenever you can go through the site, and whenever you need support for a specific uh, hardware or specific application, you can look there. For example, suppose you are developing an IoT device, and you want to integrate uh, 4G or 5G modem with your microcontroller. So you can find the library there, which is based on MQTT. So you can just make the connections. You can make the connections, and you can bring the library here. You can compile the complete MicroPython, and then you can flash the MicroPython on the target, and then it will have the support along with the old MicroPython. It will have the support for the 4G and 5G modem as well with MQTT protocol. So you can easily integrate your device with any cloud, and you can start pushing the data. You can start controlling your actuators. You can start monitoring your sensors. So that's, because of all features, it is helping us to develop quick prototypes. So suppose basically if I want to develop a IoT module which has to monitor some data, some agricultural field data, or some remote locations, sensors, or I want to control some remote locations, actuators. So everything I can do using MicroPython and the 4G, 5G modems or cellular modem. And uh, so everything is already tested and proven, and this is a high level integration. So this won't take more than a week time developing such products. And if we have to develop the same thing in a C language, then it will take approximately a couple of months. So that's all from my presentation slides. And after this, before question, I will just go to demonstrate that what are the things I have done and how this runs, how we build, how we pull the third-party libraries and build it. So most of the time, I prefer to develop everything inside the Linux environment because it's a very handy and uh, it's very, it provides us all the tools which helps me to pull or flash the things in the microcontroller. So I will just pause for a minute and just wanted to check if anyone is having any question so far from this theory part. Any question? Am I audible?
Yes.
So anyone is having any question?
I don't have any.
Okay, sure. So let's go ahead and we'll see the different development environment. So yeah, definitely it's having a different development environment because we have two different layers. So we have two different environment for developing the MicroPython code. So let's start from the application side. So I prefer to use Thorny. So this Thorny is an IDE which basically helps me to write the code, flash the code, and as I was talking about the REPL. So read, eval, and print and loop. So the bottom part, what you are saying is the prompt. So here, if you see, my device is connected to this ID via the USB port. So it is serial over USB. So the one of the most cool feature of this MicroPython is this code just resides in my PC. I'm not going to flash this code in the target, but I can run this code in the target just from my PC. So this is one of the most cool feature of the MicroPython, and this Thorny helps me to do that. And using this, we'll be seeing that how fast we can switch from one application to other application without flashing the code. So let me just show some example. The first example I'm going to show you is from uh, this is an interrupt code. So these are just few lines of code. These are the numbers of GPIOs which I have in my microcontroller. So there are total 8 GPIOs, and each are like Each provides you eight pins. So it's total 64 pins. So 64 port pins we have. So what's going here? I've just named them, and these are just print message, and this is one interrupt service routine. So just in one line of code, I'm registering my interrupt service routine. So I am specifying it must be port number A. It should be into the port number A and the pin number 3. So port A, pin number 3. So if any pulse is arriving on those pins, so an interrupt will occur. So these are an external interrupt. So I'm just going to run it. So below you can see the console. So you see these are directly running on the microcontroller. So this is rotating on the loop, and this is connected to a different microcontroller. The port A pin 3 is connected to a different microcontroller which is powered off. So I'm going to generate some pulse from that port pin. So now it is going to it is basically generating some pulses, and that is arriving to the port number port A pin 3 of my microcontroller, and you can see the interrupt service routine automatically this function is getting called. So if you see here, these libraries, these are not supported in Python. These are certain things which basically has been implemented within the MicroPython. And this particular library has been implemented as a part of enhancement. Definitely, it do support the handling and registering of the interrupt, but as a part of learning, we just wrote this code and enhanced this feature. So I'm just going to stop here. As you see, I'm not going to flash any code there. Just stop, and that's all. So we got the prompt once again. So when you see the prompt, it means this microcontroller is in standby mode. It's waiting for your input. So basically, you can just type like, let's evaluate REPL. So I say 2, iterate 2, then 3, iterate 3. If I say 2 plus 3, it prints 5. So these all are the example of REPL. So when it read 2, it just printed it back because it knows there is no further operation. It just understood just a number I have entered. So it has just noted down that number and it has printed it back. Second time also it did the same. When third time when I just added, I just typed 2 plus 3. So it understood the user is asking to do the evaluation of this one. So there is an operation mentioned as plus in between. So it has evaluated, it read, and then it evaluated, then it prints, and then it came back to the prompt once again. So it has performed the REPL. Okay, and now let's see. Let's quickly switch to a different code without flashing the code. I'm just going to run a different code now. So this is connected to, with one of the temperature sensor that is DHT11, and now it's reading the temperature and humidity. So if I try to change by just touching it, so you can see the humidity and temperature is getting changed. So it's so quick. Just a few lines of code we write, and we are able to basically get the application out. We are able to get some data out. We are able to evaluate it. So again, I stop it here, and I go to some other application. This is one of the most important, and this was one of the most time-taking interface which is actually called time of flight. So let me show from my screen. So if you see this picture here, basically we have one sensor from where basically we fire one photon towards a target, and this photon basically it's using a light. It's not the normal light. It's a laser light, and it goes and hits some targets. It comes back, and then it is read by the same sensor. I mean, in the same sensor, we have two different things. One is the LED, and it's not the normal LED. It's for laser LED. And then we have SPAD, which is basically this avalanche diodes. So that receives the data, and then based on the time it has taken, because the time it has taken to reach the target and it came back, so we know the speed of the light. So that um, using that principle, we calculated that how much different the target is from us. So using this principle, we have just developed this code. So let's see, once we run, so the driver is written in a different file, which is hidden. So that because it's a Python code, so no one should see our code. So we can definitely write the code in binary or in C or in compiled Python format. So let's run it. So you see, it's displaying the distance, and the distance is the height of my roof it is showing. So if I place some object in between, I'm putting my hand here. So you see the distance got decreased. Now if I move the hand slowly up, you'll see the distance is increasing slowly. And now I have removed my hand. So it's able to find the distance of the object. Okay, so this is one of the application. I stop it here. Then I go to a next application. So here we are just going to toggle one LED, one port pin, and we'll be monitoring the speed. I mean, we are generating a pulse here by toggling it, and the toggling speed is zero point 0.1 second. So it will be on for 0.1 second, means 100 millisecond, and it will be off for 100 millisecond. So let's run it. So it's learning. We are not printing any because print will be an overhead. So I'm not just printing anything here. So how to monitor? Let's go to the application here and see. So something is printing. Let's stop and see. So it is approximately 100 millisecond. Definitely it's 100 millisecond, right? So let's see. Okay, one hands on here. Okay, I'm just going to change the code here. So I'm just going to change the code here. I will just decrease it. So I stop and I will run it once again. And let's go and see performance. I will run it once again. And you see the size of the pulse has been decreased because we decreased the time. Now it is how much? It is 9.99 millisecond. Okay, so approximately 10 millisecond. So this proves that how fast to, change the code without flashing it. So mostly those who do research in their projects, and they're basically doing some sort of sensor interface, and they're testing their sensor, or they're writing some code for their sensor, they're evaluating some sensor. So for them, it is much easier to change the parameter and test. So I stop it here, and then I go to next application. Okay, this is a bit more interesting thing. I'm doing the same stuff here, but in a different way. Uh, I'm going to demonstrate this code because I wanted to show you how MicroPython is different from normal Python. So as I told you at the beginning, that in the MicroPython, we have the capability to access the hardware. So the electronics engineer who are basically doing your firmware coding, so might be knowing that earlier we used to perform write our C code like this. Here basically we know the hardware registers. So these are the hardware addresses of each GPIOs. Okay, and these are the offsets. So every GPIO, every GPIO is basically consist of multiple set of registers. So basically it is to like mode, like output, everything basically we need to configure it. So here we have a package called machine. This allows us to get into the hardware directly without any interaction of C code here. Most of the things which we have seen earlier is going via the C code, but here in this case, we are not going via any C code. We are accessing hardware registers directly, and we are manipulating the register directly from here. So here we have the idea is to I'm taking the port E, and I just loaded with an address of this port E. So these are the different addresses. So port E's address is this one. And I'm just configuring it. And then in the runtime, I'm just toggling this bit, which is making the port to get toggled. So let me just increase this speed. So I'm going to run this code once again, and then let's go and see what's happening there. Okay, so it's more thin. So we have to stop and see what's the width of the pulse. So it's approximately same. We have given approximately 100 microseconds. So we got 103 microsecond, which is okay because I will just tell you, because we are using a sleep function. So if we want more accuracy, so we have to write our own timer based sleep here. So this is a system sleep function, which is a generic function. So we can expect that delay because of the latencies, because we have kernel running, scheduler running, lots of middleware running. So you can expect that latencies. So if you want to basically, I'm going to show you those in the next slide, in the next example. So here in the next uh, example, we are trying to make use of timer instead of any sleep or any kind of I mean code driven or the processor driven output, because when you write onto a registers, or when you write directly into the port from your code, so you will be having a lot of sequence, because a lot of uh, different levels of calls. Okay, so here I'm just making use of timer one and channel one, which and port D6, which is basically D6. I can show you this. D6 is my bit number 4. So I'm just gonna make use of that pin, and then I just trigger it, and let's see what's happening there. We stop and then see the width. So it is showing me 50 millisecond. And let's understand what's happening there. So the total time, that's like from the falling edge, rising edge to the falling edge. You see, from rising edge to the falling edge, or vice versa. The total time period is 100 millisecond, and one pulse width is either high or low. It is 50. So let's see the code and let's understand what's happening. So here the time period, the frequency I have given is like 10. It's like 10 hertz. Okay. So more the frequency, lesser the time. So if I increase the frequency, it's 100 hertz now. So the 100 hertz is 100 hertz if I say. So it is 1 by 100 second. Okay. So that's the frequency. Frequency means the time for the total time, the complete oscillation. So a pulse, when it is wherever it is started, so it will go up and then it goes down, and when it reaches to the same state, okay, so it is the complete oscillation from the time when it started. That's the oscillation, right? That's the time period basically. So the complete time period here is 1 by 100 here. So let's run this and see. So it has been decreased because we have increased the frequency. So now we are able to see the 10 millisecond. This is the complete time period, right? This is the complete time period. So the time period is 10 millisecond. So if I reduce further, actually I'm using two machines. That's why I'm just switching between this. Okay. So we have seen various examples here. Now I just show you how we build it. So here, all the tools, basically these are the source building of the MicroPython. So here, everything is command line based. We don't have any graphical user interface here. So if we go back, here in this folder, we contain the complete source of MicroPython. So here, if you see the different, if you go and see the lib folder, so it will show you what are the different targets which it supports. So we are mostly interested in this one, and LWIP for network. And these are certain libraries supported by, I mean, needed for the interpreter, MicroPython interpreter. When you use the security stuff, you may use embed TLS, but it's not just the thing which we have to make use of. We can even want to, if you want to integrate Wolf SSL, we can integrate that here for security reason. So these are the basic libraries, and the hardware abstractions layer are there in the ports. So here, since I am interested in STM32 or Unix, so I have just checked out only these two. But if you are interested, you can basically bring the support for ESP32 or other microcontrollers as well. So if you go into the STM32, you'll be seeing the different boards it supports. So these are the general package, and board level configurations are placed inside the boards folder. So if you go and see inside it, so these are the different boards till date it's supporting. These are the different evaluation boards, third-party boards. These are all supported by the standard MicroPython, but it's not just limited to this. Even if we have our own customized board, definitely we can add those stuffs here. Apart from this, if I have to make, if I have to enhance the support, then I go to the app, and here you see these are the different supports for the different microcontrollers. But the most important is user C module. So let's see what is there inside the user C module. So inside, this is exactly like how we develop the Linux kernel. So here, if as I told you at the beginning, if suppose tomorrow you are having a customized hardware, or suppose you want to enhance the hardware for a different peripherals, so we can definitely write those code in C. So these are exclusive C code within the MicroPython, and we can basically add these stuffs. We can import this in the Python script, and we can make use of this. For example, the interrupt part of the code, which you have seen here, which I've shown you at the beginning, this one is not from MicroPython. Though we are using in the MicroPython, but this code has been developed exclusively by us to basically as a part of learning and enhancement of the MicroPython's capabilities. So I'll show you how basically we need to understand this one, okay? So I quickly go to the folder. So here, if you see the interrupt module, so this is written in C, and it is a pure bare metal code. So what we have to do from the MicroPython is we just call this function ext interrupt init GPIO underscore init. So if you see, if you remember the MicroPython script, we have called the same function. See? And this is the name of the file. So it appears like this in the C code. So this is the name of the file. You see the module, sorry. So we have registered the module with this name, GPIO ext integer. So this dot, this name, and then we need to pass certain object, because MicroPython, whatever the data types it is using, C don't understand that. So so MicroPython interpreter tells you about what are these. We have to convert this into C object. So what are the things we have sent from there? We have sent GPI number, that's an integer number. This is also an integer number, and this is a function pointer of MicroPython function. So when it reached to low level C, there we have registered these two we have just converted that to integer. These two objects we converted to integer, we recorded it, and then we configured the interrupt as usual, and then a callback function we just noted down, because this is the function pointer of MicroPython. It's a MicroPython function. So we just noted down everything here. And then whenever interrupt arrives, this is the handler in C. Then what it do? It performs a call with this number, So from which pin it has arrived, and this is the callback function. So C function in the C layer, we keep on getting the calls, the interrupt, and then it basically calls the MicroPython functions from here. So you get back your callback functions are getting called here because this is called by the C function. But there are two ways of writing this. One way we used our own C modules. The other ways you can directly make use of MicroPython. So both type of supports are there. So this is just to prove that any enhancement on your hardware can be supported by adding C code or MicroPython code. Both options are there. Next, as I told you at the beginning, that we can add any support, any extra support, or any extra support for any third-party libraries like NumPy. Oh, I'm sorry, I'm in the wrong location. So I've cleaned it. I'm just going to build this MicroPython once again. So before I build it, I show you. Okay, let me build one time. So if you see, it has included all of my source files, C source files, and then it is trying to configure its interpreter, and then I mean a build environment, a build very environment for the interpreter, and then it will start building because it is going to adjust itself based on your C code. So it's generating some configuration files, and then it will start building. The build is started now. So it's going to build a lot of source. It will take hardly 1 or 2 minutes. So meanwhile, if anyone is having any question, so you can ask me.
I just missed some part of it. I'm just trying to understand one thing. In terms of RAM and ROM consumption,
Mhm.
just the legacy C code is better or this Python, MicroPython is?
Definitely, C code is much better there if you have the RAM or flash constant, because definitely whenever you increase the language, I mean from low to high level, so the consumption of RAM and flash both will be increasing. So if you write a code in assembly language, so it will take the least amount of flash and RAM. So only the thing is, uh, from the from a decade, the cost of primary memory, which is flash and flash in the sense only NOR flash, not the NAND flash. So primary memory and NOR flash and the RAM, the cost of these things are decreasing. So in the upcoming days, you'll be seeing the controllers are having huge primary memory, which was not the case earlier. So for example, the controller in which I'm testing all this thing is having 1 MB of RAM and 2 MB of flash. That was not the case earlier. So I mean, I still feel these are huge number actually for a microcontroller. So in the future, you will be seeing all stuffs like this. So here, if you see, this is the total size of the text. If you know, in C
Yes.
code, the text is the code size actually.
Yeah, no.
Yeah, and the data. So data and BSS, these two are the part of your RAM. So base, the block segment start, that is uninitialized RAM. These are initialized RAM. So initialized RAM is just 168 byte, and this is almost 330 KB. So 330 KB plus 130, so almost half of the RAM is gone. And here, if you see, so 559 KB of the flash. So I'm not worried about this because I have 2 MB of flash. Out of that, only 559 KB is gone, and that's it. Because Python scripts are just the text format, so they are very small. So we have plenty of space. Once you flash this, we'll get a plenty of space. So now I'm going to show you something that I'm going to use a
And we
third-party
can
library.
keep it in external flash too.
Sorry?
We can keep these actually this Python files in external flash too if it consumes a lot.
We can definitely keep, but here in this microcontroller, it is hardly sometimes we connect some external flash. We can do that if we have SD card option. So we can do that. For example, if you see here in this case, whatever I have shown you the demo. So in that case, I have never placed any code inside the target. Everything I'm running from my PC. So this is a great advantage here. You can run everything from your PC. And if there is some buggy code, it won't crash your microcontroller. If it's crashing, you can just restart. No need to recover it. So I mean, earlier what we used to do, we used to flash C code. It is used to we used to find, okay, it's a buggy code. It's getting crashed every time. So then we have to go into the DFU mode to recover it, and then we were able to flash the correct code. But before flashing, we can test it. So again, if you have a question that every time should we have to run it from the PC? No, you have the option to place this in the file system of the microcontroller, but yeah, there is a constant. You have to name it with main.py. Then only it will run. If it is with some different end, it won't run. So now I'm going to show you something else. Okay, let's go back in the C module, and then I copy NumPy. This is actually a NumPy library. I just copy from here and put into the C module. And once again, I just give a build. So here, if you see, okay, so it's giving me an error because it has not generated the configuration for this ULab. It has added the ULab, which was not there earlier. So we have to do a clean build here. So now it is going to generate the configuration, keeping ULab in the mind. Yeah, I saw somewhere someone's hand was there. Someone else is also having a question. Yeah, you can ask question, Sahab.
Okay, I've already asked him during my
Okay, okay. Anyone else is having a question?
Can you recommend a board for beginners for practicing?
Okay, so if you are trying to get into the embedded system, so better I will prefer you to I will say to go with STM32H5 boards, because this is one of the latest microcontroller launched this year, and the life of this microcontroller is for next 15 years. And this is one of the most advanced microcontroller in this world, which is having a core of ARM known as M33, which is having a lot of security feature inside it. So today, even the microcontroller are getting hacked by cyber attackers. So IM33 is having an advanced security feature inside it. So you can go with this. You can go with this board. And it's having all the advanced peripheral. Its performance is much better than H7 series, which I am testing now. The reason is uh, it's having an advanced memory called instruction cache memory. So all the instructions are getting cached in that instruction cache memory before it's getting executed. So the performance is much better than even with the old. If you compare this controller with the older controller, which runs it at higher frequency. So this controller runs on 250 megahertz, but the performance of this microcontroller is much better than 480 megahertz controller because of the different level of execution, the different level of abstraction and all. So here this is still building, and let's see how much size of the code it generates. Yeah, if anyone else is having a question, then please go ahead. So now we see, I mean, here the text file, the text segment, which is the code, which has been increased from 559 to 667. So almost 100 KB of the code has been increased, and
I'm not
approximately.
sharing. Please share.
Oh, I'm not sharing the screen. Okay. So if you see the generated code now, so we have more code, more data now in the binary file. So question is how to flash it. So we use this tool called the Cube Programmer. We can just connect it. So it's connected now. I go and select the hex file, which is the most newest one. And then I say start programming. It's going to erase my chip and going to flash the code there. So now whatever the code I'm going to have in my microcontroller will be having a support of ULab, which is basically a subset of NumPy. So if I have if I need to implement a DSP application, so I can just write a few lines of script, and then I can just implement the same here. So any other question? Okay, I just quickly go through the website. Okay, so here this is the PyPy.org. Here you can see the different packages we have. So you can simply download the package and you can drop that package in this folder, user module, and you can just build it. It's very easy. And you can develop a script quickly, and you can make use of these libraries from your script. There's so many, because if you see here, you have 77 plus pages here. You have 77 pages total. So when you start experimenting, you can get your hands on in this kind of things. There's so many libraries for it. So yeah, I'm done with this. Okay, anyone is having any question, please go ahead and ask.
You can unmute yourself and ask any questions to Zafar bhai. I think there are no questions, Zafar bhai, so we can close the session in that case.
Sure, okay.
Okay,
Sure.
so thanks everyone for joining, and Jazakumullah khair, Zafar bhai, for this very valuable session. Inshallah, this will help us in exploring MicroPython further also, inshallah.
Sure, inshallah.
Yeah, Jazakallah. Thanks for the session.
Okay.